So let's continue with the Stack and Cube playlist. Before starting off, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is next greater element, but the second part of it. So before starting off this one, please make sure that you would have solved the first part for sure. You know the intuition, you know monotonic stack and everything. So what is the problem stating? It is stating that you're given an array of integers. I'll have to find me the next greater element, but there is a twist. So what is a next greater element? For every element, you look towards the right, and whichever is the first element that is greater. So over here 10 is greater, so you say that for 2, 10 is the greatest. Okay, fine. For 10, you look on the right and you say that 12 is the greatest. That is fine. For 12, you look on the right and do you find the greatest? No. This is the twist over, like the twist over here is you just don't look onto the right. If you don't find something on the right, you look in the circular direction as well, which is 2 and 10. Did you find something over here? No, I didn't find it. Thereby, the answer will be -1. For 1, you look onto the right and you figured out 11. So there is no need to look on the circular direction. Perfect. So that will be 11. For 11, you looked onto the right and there was no one. So what you will do is, you'll again look onto the circular direction. Is 2? No. Is 10? No. Is 12? Yes. Thereby, 12 will be my next greater element for 11. So the only change is, you'll have to think it as a circular array whenever you're trying to figure out the next greater element for every element. So what is the first solution that comes to my mind? The first solution is for sure, what I'll do is I'll stand at each and every element and then look onto the right. The problem is, if there is nothing on the right, I'll have to look over here as well, right? So what's the best way to do it? One of the ways is, okay, I could iterate I equal to 0 till n minus 1. And for every I, first I'll look from j equal to I plus 1 till n minus 1, which means if I'm standing at 10, I'll look from here to here, which is this particular loop. And if it is not found there, I'll again run loop from j equal to 0 till I minus 1, which is nothing but this one. That's one of the ways. Like that is the extreme naive solution that you can think of. But can I do better? Maybe I can use the concept of circular array over here. So how do I use the concept of circular array? It is very simple. So what we do is, we double the array. Not by doubling it in a real coding stuff. We just think it virtually. So what I do is, I double the array in my mind, which is, I again write 2, 10, 12, 1, 11. I have doubled the array. Virtually. Now imagine if I stand at 10, and I ask you, what will be the entire circular array? Can I say, if I take n elements from here, that will be my entire circular array? N elements? Why? Very simple. A given array has n elements. Over here, n is given as 5. So if I'm standing at 10, if I can take the 5 elements, which is this one, this will be my circular array for sure, right? Okay. Or do I need to double the array? That is the question. I don't need to. What I will do is, I'll try to think hypothetically. Okay. Let's see how. N is 5. If n is 5, this index is 0, this is 2, this is 1, this is 2, this is 3, this is 4, this is 5, hypothetically 5th index, hypothetically 6th, hypothetically 7th, hypothetically 8th, hypothetically 9th. So whenever the value of I comes out to be 5, right, whenever you're traversing, I don't have a 5th index. So what you will do is, you'll say 5 modulo n. which is 5, that'll be 0 because the value of n is 5. And 0 is nothing but this index. And if you look at 6, 6 modulo 5 is 1, which is this. If you look at this, 7 modulo 5, where 5 is n, is 2, which is this. So if you can just play with the indexes, you don't need to double the array in a data structure. You can just do it hypothetically. Okay, fine. You understood this, right? So what I'll try to do is I'll try to do it in the code. That will get into your brain in a much better way. Okay, so what I'll try to do is I'll try to go for each and every element. So first, I'll take an NG, which is of size n. After that, I'll try to traverse from I equal to 0 till n minus 1 because I need for each and every element. So I need to traverse each and every element. So in a circular array, so it will start from I plus 1. And I can say that it will go till I plus what? That is my question. Let's see. If I'm standing at 1, I'll go till 5, which is typically 1 plus n minus 1, where n is 5. I plus n minus 1. Yes, it is. So I'll go till I plus n minus 1. Why minus 1? Because you're traversing from here. So basically leave out one element. Okay, done. So I say, okay, what is my original, like what is my index? Can I say the index hypothetically is j modulo n? That is my hypothetical index. Because whenever I'm at 1, that's fine. Whenever I'm at 2, that's fine. 2 modulo 5 is okay. 3 modulo 5 is okay. 4 modulo 5 is okay. But whenever I'm at 5, I need a 5 modulo 5 to get the value, okay? So can I say, if array of index is greater than array of I have got my NGE for this I, which is array of index. And at the same time, I can do a break. Perfect. The for loop ends and the sends. And eventually, I can return the NGE. So I've done a circular array. Very clean. Very, very clean. Right? What will be the time complexity? Definitely a big of n over here. And definitely another big of n over here. So I can say that the overall complexity is a big O of n square. And the space complexity is big O of n just in order to store the answer. Nothing else. So I was able to solve this using big O of n square. Obviously, the interviewer will not be happy because we are taking big O of n square and he'll ask you to optimize it. So we need to optimize n square. And we've already done the optimization in the next greater element. Now this is next greater element part 2. So I know for sure I could go somewhere near about big O of 2n by using the monotonic stack concept. Okay, so I need the monotonic stack concept. By using the monotonic stack, in the next greater element, we were starting from the last element. And for the 11, I was looking in the right. But this is a circular array. So I need these elements in the stack. I need these elements in the stack, but then not. So what I'll do is hypothetically double the array. So if I hypothetically double the array, it will be 2, 10, 12, 1, 11. Hypothetically doubled the array. If I have to write down the indexes, this will be 0th index, 1st index, 2nd index, 3rd index, 4th index, 5th, 6th, 7th, 8th, 9th index. Right, that is what it will be. Maybe I can simply draw another square box so that it doesn't get mixed. Perfect. So what is the last index? The last index is nothing but 2 into n minus 1th index, where n is 5. Basic maths. Fine. Now can I say, whenever I'm at 11, I'll have these elements traversed. Only if when I start at the last element. Fine. So what I'll do is, I'll take the stack and I'll be storing everything in the decreasing order as we did in the next greater element. So this is my stack. So let's start from the last element. What do we have? We have 11. Do we have anything in the stack? No. So maybe I can just put it into the stack. And the next greater element for this one, do I need? No. I need for this one, I need for this one, I need for this one, and this one. I need the next greater elements of these elements. Nothing else. Fine. I'll move to 1. What is the top of the stack? 11. That's greater than 1. Perfect. I'll put 1 over there. I go to 12. The top of the stack is smaller than 12. The top of the stack is smaller than 12. I just take both of them off. And I put off 12s into it. Perfect. After that, I go to 10. It is okay. Yeah. After that, I go to 2. Still okay. Perfect. After that, when I go to 11, I have a 2 in the top of the stack, which is smaller. I have a 10, which is smaller. So what I will do is I'll take them off. For this element, I need the NGE. How do you know it? Because this index, which is lesser than 5, the index is lesser than the n. Thereby, I need the next greater element of this one. Fine. So what will be it? That will be 12. And I can take up 11 and I can put it over there. And after that, I go to 1. Okay. 11 is okay. That can be my next greater element. So I'll take it and I'll put it 1 into the stack. After that, I go to 12. For 12, this cannot be, this cannot be, this cannot be. So I take all of them off. Yes, I take all of them off. 1 goes, 11 goes, 12 goes in 3 steps. Thereby, the answer will be -1 because the stack is empty. Right after that, I go to 10. And whenever I go to 10, by the way, before going to 10, please make sure you put 12 back. After that, I go to 10. And when I go to 10, the stack has 12. So 12 will be my answer. Put 10 and then go back to 2. Whenever I go to 2, the stack has 10. That can be my answer. Put 2 and the traversal is completed. So yeah, that will be it. Super simple. Hypothetical stuff. Okay. So what will I do? I'll do a very simple thing. I'll write the code. Yeah. So I need to return a list. So a vector list, whichever language you're using. I'll say find NGE again. And I'll be given an array. How do we do it? We need a NGE array which stores all the next greater elements. We need a stack for sure. So we can define it as stack st. We traverse from the last index in the circular array, hypothetical. That's 2n minus 1. And we go on till 0. Perfect. Okay. What is the next thing? I look in the stack and I try to maintain its monotonic nature. Okay. So I say while stack is non-empty, while the stack is non-empty, and whatever is at the top of the stack, that should be lesser than equal to array of whatever index modulo n, because that will give you the value, because I is a hypothetical index. You haven't doubled the array. Okay. And this is the case. I do a stack.pop and we are done and dusted. The small elements go and the monotonic stack order is preserved. What after this? Okay, we're done with this. We need the NGE for sure. Now I know one thing. If I is lesser than n, then only I'm looking for a NGE, correct? So if the stack is empty, if it is, we say NGE equal to, or maybe we could write it in a better way. We could say NGE of I, because if I is lesser than n, that's fine. If the stack is empty, that will be -1, or else it will be whatever value is at the top. Done and dusted. And right at the end, we say stack.push what? Array of I. Please make sure modulo n, because you're dealing with hypothetical indexes. We didn't do a modulo n over here because it is lesser than n. While loop is complete. The for loop is completed. And at the end of the day, I could end up returning NGE, and that is done. The function is completed. What about the time complexity? Again, this at max can be 2n elements. And at max, you could end up removing 2n elements from the stack. You remove those elements that you push. At max, you push 2n elements. So at max, you could remove 2n elements. So the time complexity is bgo of 4n. Please mention that explicitly to the interviewer. He'll be super impressed. What about the space complexity? We're ending up taking bgo of 2n in the stack. In the stack, at the worst case, it might be. It will not be, but it might be. I'm just saying. And another bgo of n in order to store this one. Again, this cannot be ignored. Please don't modify the array in order to return the answer. Please don't do it. So yeah, that will be it for this one. I hope you understood the concept of circular array. How you do not double it, rather you hypothetically use indexes in order to have the circular array in your mind. So that will be it for this one. So if you're still now watching and you've understood everything, please do consider giving us a like, and if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye, take care.
Whenever your heart is broken, don't ever forget you're golden.